hey, if I hook up a capacitor to a battery, let's say I've got this D battery here, and this side's positive and this side's negative, and here I have a parallel plate capacitor, and my intention is to put a wire between here and then a wire between here, and as soon as I connect that, see, as soon as I connect that, the voltage on the capacitor will gradually increase like this. Voltage will go whoop, like this and approach some maximum level, probably the voltage of the battery, if this is a function of time. But if I'm going to also want to know what's happening to the current, see, the current immediately will be huge. There'll immediately be a very large current. As soon as I connect that, there'll be a huge current, and then the current will taper off and approach zero, where these guys are acting very differently, right? The current in this circuit is going to be falling to zero, and the voltage will be rising up, and that's because we can intuitively understand this, because as soon as I make this connection here, there's no force against the electrons initially going this direction. There's no force initially against the current going that direction. But as the capacitor becomes more and more charged, then the voltage difference between the capacitor and the battery is approaching zero, because, well, the voltage of the the voltage of the capacitor is approaching the voltage of the battery. So we want to think now about what happens if instead we connect a capacitor to an alternating source. I'm going to connect a capacitor to an AC source, and I want you to think about what this means. See, if I connect it to a DC source, then the capacitor actually looks like a break in the circuit. It will just prevent any current from flowing. But if I connect it to a very fast AC source, it's almost as if the capacitor isn't there, because as soon as I begin to charge the capacitor, the current from the source changes direction and then discharges it, and can charge it and discharge it and charge it and discharge it. So it's just as if there were a wire right here. So let me summarize that little observation. I will say at, oh, and of course, I'm going to use omega to symbolize how fast I'm sloshing right here. This is the frequency, the angular frequency of my AC power source. At low omega, capacitors look like what? And at high omega, this is very important, so I'm going to ask you to fill those in. You have to think about what it means. Capacitors, and I don't need to say look, I could say they act like what? In a circuit. This is very important to think about. In a DC circuit, a capacitor looks like a break in the circuit. And so at low omega, that's what capacitors look like. It looks as if the circuit is broken. But at high omegas, sloshing back and forth, the capacitor doesn't affect the sloshing at all, assuming the capacitor is large enough, right? So that it doesn't reach its maximum voltage very quickly. Capacitors that are tiny reach their maximum voltage very quickly and could still impede the flow of charge through this part of the circuit. Of course, there aren't actually charges going that direction or that direction. It's just everywhere along here and everywhere along here. So as long as you're outside the capacitor, it looks as if there's just a wire right there. So here we put wire, and there we put break. Or here you could put short, and here you could put break. A break and a short are very different things. Think about that for a moment. Now, as we go into this, we're going to have to do a little bit of calculus, and I think that's probably very good for us. So let's do it. You know that the voltage across a capacitor is the charge on the capacitor divided by its capacitance. And this charge is actually the integral of the current going into the capacitor. So as current goes into a capacitor, it fills up the capacitor, and that's what gives the capacitor charge on its positive plate. So let's write that again. The voltage on the capacitor is charge divided by capacitance. So that's going to be, well, it's going to be the integral, well, it'll be 1 over C times the integral of current over time. And with my AC generator now, I'm going to say that I have current that does depend on time, and I'm going to say that the current is, well, this is current as a function of time. It's going to be I max times the sine of omega times t. That's my current. I plug that in right there and see what happens. It's going to be some really enjoyable calculus. 1 over c times the integral of I max times the sine of omega t over time. I max is a constant and it pulls out, and we just have to do the integral of the sine of omega t. It gives us the negative cosine, and then we have to do the chain rule for integrals. Oh man. So we get negative I max over c, and then we have cosine of omega t, and we've also got to note what the integral of that sucker is, and that would be, oh man, I think I'm going to get divided by omega right here. So that's really lovely, and I could write it just slightly differently. I'm going to write it as, oh gosh, well this is negative cosine here, but I happen to know that negative cosine of theta is the sine of theta. This is really lovely. Sine of theta minus pi by 2. All right, so that's a substitution I'm about to use, and I'm just going to clean things up a little bit. I'm going to say that this is 1 over omega times c times the maximum current possible times the sine of, well, what do we have to put? We have to put omega t minus pi over 2. This equation is a very powerful equation. We call this constant here a phase shift, and that's related to the term phasor, of course. And what we're seeing is that the phasor for voltage is not facing the same direction as the phasor for the current. So first of all, we can identify some maximum values. When the sine function is at a maximum, it just disappears, it becomes 1. So then we say that V cap is 1 over omega c times I max on the cap. So that would be the maximum voltage, so I can say V max is 1 over omega c times I max. I hope that you believe that particular observation. And I want to make a substitution also because it's one of my favorite electrical equations. I like the idea of a resistor where V is I times R. And for a resistor, we also find that V max is I max times the resistance of the resistor. So what if capacitors acted kind of like resistors? And they sort of do, because they are sometimes able to act like a line in the circuit, a short circuit. Sometimes they're able to act like a break in the circuit. So that's sort of a resistance. It's not exactly a resistance. We call it a reactance. So I want to say that this is V is equal to I times something. So I'm going to define 1 over omega c to be the reactance of a capacitor, and it's abbreviated with the letter X. This is the reactance of the capacitor, and you'll find that it actually has the same units of resistance. This is radians per second, and that is the capacitance in farads, and you get units of ohms. Wow, go figure. Try that out. It's really beautiful. So we have this analogy of Ohm's law for, well, we can write it here. The analogy of Ohm's law for capacitors is that voltage on a capacitor is, and sorry, I have to put maxes in here or RMSs in here because it's not an instantaneous equation at all. It's going to be I max times the reactive capacitance. Now, my next plan is to show you how this works. No, I'm going to have to use a different page because this is really important stuff. I'll set up my axes, and I've got Y and X, and this is where my phasor is going to live. Before I go on, though, I want to remind you this is what the phasor of a resistor looks like. Starts here, and if the voltage is max, then the current through the resistor will be max at that same time. So right now, I'm saying, what is the Y component gives the value. The y component of the phasor at any instant in time gives the actual value of that variable. So right now, I've got no y component for anything, and now I've got maximum. Remember, this is everything here is rotating at omega. So that's the frequency of my power source, and as I reach this point right here, I get maximum value for current and maximum value for voltage. And that's a resistor. And then I get none, and then I get negative current and negative voltage, right? Because you're pushing the other way, it's going the other way, and then I get none again. And so if I draw this graph for a resistor, I'm going to find that the voltage might do this, and the current, what do I want to use for current? Let's use orange for current. The current would do this, for instance. Where these guys have the same time dependence, and they are, we can call these in phase, and they differ only by this, this Ohm's law relationship. This is going to be, let's see, this is V, and this level is V max, and the orange is I, and this value here is I max. And we can define I max by Ohm's law. V is IR, so I is V over R. I max is going to be V max divided by the resistance of my resistor. It's time to go to capacitors, though. So resistors are really, really pleasant. Everybody likes resistors because they're super simple. It's time to go to capacitors. And in a capacitor, let me get you the same idea of a graph. In a capacitor graph, if the voltage starts out, well, let's see. I'm actually going to say that the voltage on the capacitor is going to start out, I mean, it really doesn't matter where we start. We'll just start here. We'll just go voltage big, voltage small. I'm zooming in a little bit. I changed my angular frequency so that you can study this a little bit better. So this is my voltage, and this is all as a function of time. Sorry, I should have labeled that up there. Now, the interesting thing about a capacitor is that if you have a large voltage across the capacitor, then that's when the current actually stops. So let's go back to this diagram right here. As I'm putting a really large voltage across the capacitor, that means the capacitor is fully charged because Q is CV. And when Q reaches a maximum, that means the capacitor is going to be impeding the flow of charge. You won't have any charge flowing at that time. So the current is zero when the voltage reaches a maximum. And we can also argue that the current is zero when the voltage reaches a minimum. So we're going to have these zeros right here. I want to also say that if the voltage is decreasing, then you can imagine that we'll be, what are we doing here? This is going to be a graph of current ultimately. And I'm going to say that the current will be going the opposite direction as the voltage decreases. So there we've got voltage at a peak, and the current now is going below zero. And then it comes up and goes above zero, and comes down and goes below zero, and comes up and goes above zero. So you've got this very interesting pattern. Notice in this case, we can look at it in terms of current. The current is a minimum when the voltage across the capacitor is zero. And the current is zero when the voltage across the capacitor is very negative. If the voltage across the capacitor is very negative, then you can bet that that will induce a current to start going the other direction. So it's sloshing. But the key fact is that they are out of phase. We've already seen that they're out of phase. I want to remind you that they're out of phase by this equation right here. It says that the voltage on a capacitor is the current max on the capacitor with this stuff right here, this reactance, but it's out of phase of the same omega. It's minus pi over 2, or 90 degrees, or it's a quarter revolution out of phase. That's what it means to be a quarter revolution out of phase. These guys are in phase, and these guys are a quarter out of phase. So I'll say pi by 2 out of phase. Hi, Kira. Hi. And if I take this capacitor phasor, you see that initially, if I started out like this, I didn't actually start it out like this, but look at this instant right here. This is the instant right here where the voltage, that's my purple, is a, oh no, sorry, this is maximum current. Oh, that is right there, yeah, good. So I get maximum current initially before the capacitor is charged, right? And there's no voltage on the capacitor as I start. So I start charging the capacitor, there's a huge current, and the voltage rises up. As I'm going to here, the voltage is rising up because I'm charging my capacitor. Boom! Now the capacitor is fully charged, so the voltage is huge, but the current has dropped to 0 because the capacitor is fully charged. And the power supply starts saying, no, let's go the other direction. So the current actually starts unloading, going away from the capacitor and back towards the power supply. And that's here right now. And now we have no voltage. See, the Y component of this phasor right here is at 0, but we have a very negative current. And if we continue going counterclockwise, right here, for instance, we've got no current, but we've got a very, very negative voltage. And as I continue spinning this around, you see how these two things interact. Which one is leading? Would you say that the current is leading the voltage, or that the voltage is leading the current? Now, take that answer that you got right there, the voltage leading the current or the current leading the voltage, and see what you think if you look at this. Which one of these does it look like is leading? Does it look like the voltage is leading here, or the current is leading? I mean, I guess if it's a race that direction, then it looks like the voltage is leading, but it's not. What we're doing is we're scrolling across this. So we're saying at this instant right here, we've got that, and then, oh man, see, that's going down, and now that's going up. Which one looks like it's leading now? It looks to me like the orange is leading, because the orange leaps up, and then the purple's like, oh, okay, we can go up. And then the orange shoots down, and the purple's like, okay, we can go down. And then the orange shoots up, and the purple says, okay, we can go up. All right, so that's why it's consistent to say that the voltage lags the current for a capacitor. And that'll be our final statement here. Voltage lags current by a phase shift of pi over 2. They are 90 degrees out of phase. I'm gonna go get some lunch. I think you should have some. Connect that, see? As soon as I connect that, the voltage on the capacitor will gradually increase like this. Voltage will go whoop, like this and approach some maximum level, probably the voltage of the battery, if this is a function of time. But if I'm going to also want to know what the current in this circuit is going to be falling to 0, and the voltage will be rising up. And that's because we can intuitively understand this, because as soon as I make this connection here, there's no force against the electrons initially going this direction. There's no force initially against the current going that direction. But as the capacitor becomes more and more charged, then the voltage difference between the capacitor and the battery is approaching 0, because, well, the voltage of the the voltage of the capacitor is approaching the voltage of the battery. So we want to think now about what happens if instead we connect a capacitor. Hey, if I hook up a capacitor to a battery, let's say I've got this D battery here, and this side's positive and this side's negative, and here I have a parallel plate capacitor, and my intention is to put a wire between here and then a wire between here, and as soon as what's happening to the current, see, the current immediately will be huge. There'll immediately be a very large current. As soon as I connect that, there'll be a huge current, and then the current will taper off and approach 0, where these guys are acting very differently, right?